All right, guys, we hired 2 naval architects, paid them $1,000 each to have them tell us the best way to fiberglass the houseboat back together where we cut it in half. And I think we might have gotten scammed. So today we're gonna do some redneck science, do some testing, and see if the numbers that they came up with make any sense at all. So for the uninitiated, this is a series we're doing on restoring our old houseboat, the Enigma. We chopped it in half, we took a piece of another houseboat, we're trying to fiberglass it in the middle to take the boat from a 43 foot to something like a 51 foot. Now, some people in the comments, and even some friends and family, had some concerns about this piece that we're fiberglassing in and how strong the whole boat would be after we do that, and that's valid because we don't want the thing to break in half out on the lake, right? Now, in some previous videos, I showed you guys how I was going about getting the pieces of the boat ready to fiberglass, the scarf ratio. I showed you guys this a bunch, coming up with a 20-to-1 ratio of grinding the pieces of boat back and then fiberglassing over the top. So I took all of this data and I posted it on a boat building message board. Now, a message board is something that no one under 30 is gonna have any idea what it is, but the people there started to chime in and they said, really, I just need to have a naval architect look at this and tell us what to do. All right, before we try and hire these naval architects, I'm gonna show you guys exactly what we did and what we're trying to figure out. So here's a little 3D printed side view of the houseboat, and here's what we did. Now, as you guys know, we took the houseboat and we chopped it in half for no good reason. That's pretty much how it happened that day. And so after we split the houseboat in half, we brought a piece of an identical houseboat, stuck it in the middle, and now we're trying to figure out how to fiberglass this back together so that it is as strong, or actually we want it stronger than the original boat. What we're gonna ask the naval architects to do is simulate a worst case scenario of stresses on the boat. And one way they do that is if you're in the ocean for some reason in the houseboat and the wavelength is 50 feet, and there's some giant waves, so you're only supported at the bow and the stern. And then you've got something like 40,000 pounds of the boat with no support, just trying to pull it apart at the bottom. So that's tension on the bottom of the hull, just trying to rip the fiberglass apart. And that's what we want to find out, is what forces would cause the boat to split in the middle like that. So I figured we'd hire 2 naval architects and then we could compare the results of the 2, make sure they kind of match up. So oddly enough, you can't just get online like you're hiring an electrician or a plumber for the house and find a naval architect. So after looking around for a while, I found a couple sites where you can hire freelance engineers, and a lot of them said they're naval architects, so I figured that might be a good way to go. I made a pretty simple job description on here. I said we're modifying an existing houseboat. I said we're inserting an 8-foot section of the same model boat, and then I linked off-site to a big thread with a bunch of pictures and all kinds of descriptions of the previous testing I've done, so that someone would have to actually go click on that and read through it to really understand what we're doing. And after I made the posting, within like 30 seconds, 15 or so applications came in. So right away I knew these are people with bots running or some AI set to just automatically respond. The second guy to post a response here, it says, I read every single part of your job details and understand you're searching for a web development expert. What? This person here, hi, my name is Rabia. I am working in the writing industry since 2011. What? This guy says, I am a PhD holder, which means I am highly capable to tackle this project. Content editor. No, we're not looking for a content editor. So after all these came in, I figured I'd ignore them all, give it a couple days for people maybe to actually go read through what I posted, see if anyone actually came back with a good response. So after a few days, we had 31 proposals averaging around $1,038, and a couple of them actually sounded like they knew what they were talking about. I'm gonna use Reservoir Dogs names here instead of the real people's names. Mr. Pink, we're gonna call him. He sounded like he knew what he was talking about, said he had experience with fiberglass boats, was a naval architect, and he immediately asked for the files. Because if you've seen some of the previous videos, you know I've drawn the boat up in SketchUp, and I've got the old boat, the new boat, every dimension you would ever want. And this person actually replied back and showed that they were able to open the files. So I thought, okay, this is an actual real person. Sounds like they know what they're doing. Okay, the next guy, we're gonna call him Mr. White. In his proposal, he says he's familiar with the nuances of scarfing and bonding hull sections together, having overseen numerous modifications. So that sounded great. Both of these guys were about $1,000, so we settled on that for each one. So I was in for $2,000 hiring both of these guys. And then I waited. Now, over the next month, I'd get messages every few days from one or the other, and they sometimes would ask for additional measurements of the boat. And then finally, after a month, each one of them sent me their reports. and they are, to say the least, very interesting. Mr. White sent his file first. He shows kind of a redrawing of the boat. It's got a side view here and weighs between 29,000 and 42,000 pounds. He shows another drawing here of the side of the boat with an 8-foot section in the middle, so that makes sense. Now here's where it gets interesting. He shows a side view of the boat and shows that he's putting forces on the boat at the front and the back. So where's that little model of the boat? Okay, what Mr. White is doing is basically saying a worst case scenario, if there's a wave in the middle of the boat and it's trying to pull down at the bow and the stern. On the next page, he's got a diagram showing the scarf ratio, and he says the maximum braking force applied to the connection is 77,000 PSI, which sounds really high. And then he says when connecting the hull with a 1 to 20 fiberglass scarf, the theoretical max braking force is over 300,000 PSI. And then he shows a stringer layup schedule, which is not really a stringer layup schedule. These are just a couple screenshots off Google, and that's it. That's all we got. Mr. White provided an ANSYS report. Now, ANSYS is an actual piece of software that engineers use to do finite element analysis. I had to convert the units over to see if they make any sense, because everything's in metric, of course. They show 3 parts of the boat in here. The first one weighing 4,759 pounds, the other section weighing 2,204 pounds, and then the middle section is 4 million pounds, which makes no sense. But maximum shear stress. Okay, so these are in pascals. I converted them to PSI. So the maximum force would be 1,477 PSI, which is a far cry from what the other engineers said would be 77,000 PSI. So Mr. Pink is saying that it would be about 50 times less force than Mr. White. That's way off. The interesting thing about Mr. Pink, if you go back and actually click on his name here, where we were messaging back and forth, you get a nice Oops 404 page notice, so he's gone off of this website. I'm not sure if he was ever a real person or not.
Son of a bitch! Give me a drink! One more night! On this camping thing! Son of a bitch! If I drink it clean, I'm gonna drink my life away.
So the two naval architects' numbers are not matching. They're not anywhere close. The one that says the force on this connection would be 77,000 PSI is basically saying, like, for this little 1-inch square section here, there'd be 77,000 pounds pulling on it. So pretty much like a fully loaded semi-truck. Doesn't make any sense. I was on the US Naval Academy's site reading some of their course materials, and they said a simplified way to model the stresses on a boat is to model it as a rectangular box, and then you can use beam theory to figure out the stresses. So the same way you'd figure out the stress on like the I-beam out there we use to lift the engines in and out of the boat. So that's what I did. I modeled this as a 10-foot by 10-foot and 50-foot long beam supported only at the stern and at the bow, like if it was on a jack at each end. I said it weighs 50,000 pounds, and then I added 5,000 pounds worth of like people in the very middle of the boat. So it's kind of like the worst case scenario of stress, and it came out to 475 PSI that it would be trying to pull apart the bottom of the hull. And 475 PSI along the 60 square inches that makes up the bottom of the hull here would be around 28,000 pounds trying to pull the hull apart. So that sounds more reasonable than the 4 million pounds that the other naval architect came up with. I read an article on some fiberglass testing, and what they did, they took brand new fiberglass, they ripped it apart in a machine, and they got 26,000 PSI of tensile strength out of it. Then they took some samples, they did a 12-to-1 scarf, and glued them together with epoxy. They got 80% of the strength back of the original fiberglass. So what I think we can do is do our own redneck testing with some samples from the houseboat, see if we can get anywhere close to that. So I'm gonna cut a chunk of the catwalks out here and we'll slice it up into the test strips because we're gonna replace these catwalks anyway with aluminum or something else. I'll cut enough samples that we can do a test on the original fiberglass, a 12-to-1 scarf ratio, which is what they normally recommend, meaning if the hull is a 1/2 inch thick here, you bevel it back 6 inches. But what I've done on the houseboat so far is a 20-to-1 bevel, which is supposed to be stronger. So here where the hull's a 1/2 inch thick, I've scarfed back 10 inches. So we'll do 3 tests. The original houseboat, how strong is that fiberglass? A 12-to-1 ratio, and a 20-to-1 ratio. Got me an old cheap Amazon crane scale. It's rated at 1 metric ton, which is 2,200 pounds. We'll find out. It's pretty cheap. And then I've got our old standard engine hoist here. It goes up to 4,000 pounds. So I think we can rig something up where this can lift and rip fiberglass apart. Maybe. Let the redneck engineering begin.
My papa's son wandering out a smoking gun. Now some of you would live through me, then lock me up and throw away the key. Or just find a place to hide away and hope that I'll just go away. But I feel alright. I feel alright tonight. Feel alright.
All right, here's what I built. I found some 6061 aluminum bar, got holes drilled through that. I've got these two plates here, and I scored them this way with the sander. That way there's some friction here, because this is what will be clamping onto our test pieces. And then the bar just adds a lot of extra support. I've got 7/16 threaded rod, some grade 8 bolts, so that'll clamp down pretty good, I think, and I've got 2 of those. So we'll get our test pieces clamped in, and then we should be able to yank them apart, maybe.
Yeah, I feel alright. I feel alright tonight. Yeah, I feel alright. Feel alright.
Get my safety glasses on so I don't get a fiberglass shot in my eye. All right, here we go. Sample number 1. All right. Oh, right past 100 real quick. We're already past 300. Okay, we're at 600. I'm gonna get my cheater bar on. Now I can't see what it's at from over here. 900. Okay, that's better. 1,400. I don't really want to be, I'm gonna put this damn barrel between me and the thing so I don't get shrapnel shot in my face. Woo. Oh, there went the scale. Okay, that was crazy. So it broke at 1,857 pounds. The scale tried to launch off into outer space. The zip ties I had holding it onto the hook, those didn't work. So I've modified the setup a little bit. I've got the scale through a chain link now so it can't fly off. I've got some rope holding it down a little bit so that hopefully it doesn't try to fly around. I'm gonna keep staying behind my 55-gallon drum here because that was a lot of energy that got released. When it broke, it shook the camera on the tripod over here on the concrete, so it must have sent a little shockwave through the concrete or through the air. I don't know. It's kind of weird that it made the camera shake like that. Yeah, so sample number 2. Let's see what it does. Okay, is the scale still working? It's zeroed out. Yeah, there we go. Okay. Get behind the safety of this 55-gallon drum. All right. Oh, good. Okay. Scale didn't try to launch off into orbit. All right, that one broke at 1273. Same thing, we've got 2 bundles here that pulled it apart, and rope kept the scale from trying to shoot off in outer space, so we'll keep going with that. On to sample number 3. 1,400, good Lord. Ooh, okay. All right, 1,569 pounds on that one, and check out how much of the fiberglass it pulled out of that thing when it broke. So it's an interesting failure mode there. Okay, pretty cool results after all that. So I'll put all the numbers up here on the screen. The average pound force required to break these came out to 1,636 pounds. Comes out to an average of 11,685 PSI. So we're not in that 26,000 PSI from the magazine article, but this is a 40-plus-year-old boat. It's this woven old polyester fiberglass, so, you know, that's still pretty strong, because if you do the math, the bottom of the hull, just the very bottom, which is 10 feet across and a half-inch thick hull, at 11,000 PSI, that's 700,000 pounds that would be required to rip the boat apart. So that seems pretty strong. Sounds crazy, but that's the math. So. All right, so all the pieces cured overnight. We've got the same epoxy on them that we're using on the houseboat. So here is a test sample of a 12-to-1 ratio. So it's 1.7 inches of overlap. And then here's a 20-to-1 overlap. That's 2.8 inches of overlap. So in theory, this should be stronger. So let's get going. Okay, here's all our test samples. We're gonna start with the 12-to-1 ratios first. First test sample with the 12-to-1 scarf ratio. Get some tension on her. And we're trying to get as close back to that 11,000 PSI as we can. I'm not that confident that we're gonna get close, but find out. No clue what we're at because I can't see the scale from this side. Damn, 900 pounds. What the heck? Okay, that scared the shit out of me. What did we break at? Let's find out. Okay, that's a pretty shocking result for me. So it failed at 1,434 pounds, and it did not fail in a shear failure. It failed in the old original fiberglass down here. So everything that we epoxied together right here held together fine. So the epoxy is stronger than the original fiberglass. So that is pretty shocking. Let's keep testing. Okay, so after all the testing, I crunched the numbers. I've got it in Excel. I've got some charts. I won't bore you too much, but I've got it color-coded. So orange are the original pieces of fiberglass that we tore apart to see how strong the original hull is. Blue are the pieces we glued together with a 12-to-1 scarf ratio. Green are the pieces with the 20-to-1 scarf ratio. So the original pieces of hull averaged 11,686 PSI before they tore apart. A 12-to-1 bevel averaged 8,662 PSI before they tore apart. And the 20-to-1 bevel averaged 9,450 PSI before they tore apart. So if we consider 100% strength for the original pieces of boat, the 12-to-1 bevel got us back to 74% of the original strength, which is pretty good. And then the 20-to-1 bevel got us to 81% of the original strength of the boat. And then last night, I did it in here with the flickering lights. I did a piece of a 20-to-1 bevel, but I did an extra piece of fiberglass over the top of the repair, and this broke at 2,000 pounds, which is over 14,000 PSI, which is stronger than the original fiberglass. So if we repair the houseboat with 20-to-1 bevels, and then we do extra fiberglass over the top, it should be stronger than the original boat. Now, neither naval architect gave us a stringer layup schedule or where we should place bulkheads here in the houseboat. So what I did, everyone on the boat message boards recommended this book, Boat Strength, and it's by a famous naval architect, and he's got calculations in here for everything you need to build the boat, depending on what you're doing with it. So here's a real quick example, bulkheads. It's got a pretty simple formula. For the original 43-foot houseboat, we should have had 7 the horizontal supports in the boat. So this back wall for the engine room, that was one bulkhead. And then way up at the front where the stairs are, that was the other one. So there only was 2 bulkheads in this whole boat. And that's why the floor boat up in the middle, to the point where we couldn't open some of the doors, and that's why we brought the houseboat here in the first place to start restoring it. And now that we're increasing the boat length to around 50 feet, we're gonna need 8 or 9 bulkheads. So, every 4 feet or so, we'll have the horizontal supports going across the bottom of the hull. So this thing's gonna be stronger than it was when they first built the boat. So did we get ripped off by the 2 naval architects? Yeah, I think so, but it kind of forced me to buy that book. Over the past month, do a lot of reading, a lot of math. We built that test rig, tested those pieces out, and now I feel a lot better about fiberglassing the boat together and it being as strong as it was from the factory, or even stronger. So I guess that's the one good thing that came out of this. Now, if you or someone you know is an actual naval architect, I'd still like to have all this math validated at some point. So let me know in the comments if you've got any other ideas too. And I appreciate you guys hanging out with us as always. We'll see y'all next time.